Hello! Welcome to today's lesson on understanding how observation methods can be used to comprehend the nature of the universe. Today, we will acknowledge the vastness of the universe and how daunting it can be to grasp its size and complexities. Then we will see how early civilizations' night sky observations laid the groundwork for modern astronomy. We'll explore how inventions like Galileo's and Newton's telescopes expanded our view and the limitations posed by Earth's atmosphere. Finally, we'll look into instruments like radio telescopes and infrared detectors that reveal different aspects of the universe. We will discuss the ongoing advancements in observatories, instruments, and techniques that continuously expand our understanding of the cosmos. So far, you have become familiar with the concept of galaxies and appreciate the broader context of the universe as a collection of countless galaxies. Building on this foundation, we'll delve deeper into how modern observation methods enhance our knowledge of the universe. Let's get started. The universe is unimaginably vast, consisting of billions of galaxies, each with millions or even billions of stars, planets, and other celestial objects. To grasp the vastness of the universe, imagine this: light traveling at 300,000 kilometers per second. Takes over 4 years just to reach us from the nearest star, and yet that star is only one among billions in our galaxy, which itself is just one of trillions of galaxies spread across the cosmos. Grasping its sheer size can be daunting, but through observation, measurement, and analysis, we can begin to understand its structure and components. Observation is the foundation of astronomy. For centuries, astronomers have relied on observing the sky to understand celestial bodies and cosmic phenomena. In ancient times, astronomers used nothing but the naked eye to map the stars, track the movement of planets, and predict eclipses. However, today's astronomers have a wide array of advanced tools and techniques that allow us to gather precise data on distant objects. By observing the universe, we gather information that can be measured and analyzed to answer fundamental questions about its nature and origin. In ancient civilizations, observation of the night sky was deeply connected to daily life, guiding agricultural practices, religious ceremonies, and navigation. Cultures like the Babylonians, Egyptians, and Mayans developed calendars based on their observations of celestial cycles. The Greeks, notably, made significant advances in understanding the night sky. Greek astronomers, such as Ptolemy, developed a geocentric model of the universe, where the Earth was believed to be the center, and all celestial bodies, including the sun and stars, orbited it. Although this model was later proven incorrect, it was instrumental in advancing early astronomy and stimulating debate and discovery. These early observations laid the groundwork for later scientific approaches, shifting from mythological interpretations to more empirical methods. The meticulous documentation of star positions, planetary movements, and celestial events became the foundation for scientific astronomy. The development of the telescope in the early 17th century marked a turning point in astronomical observation. Galileo Galilei was one of the first to use a refracting telescope, which uses lenses to gather and focus light to make groundbreaking discoveries. His observations of the moons of Jupiter, the phases of Venus, and the rugged terrain of the moon challenged the prevailing geocentric view of the universe. His work provided crucial evidence supporting the heliocentric model, where the Sun, rather than the Earth, is at the center of the solar system. The phases of Venus are the changes in light on the surface of the planet that make it appear to wax and wane like the Moon. Though Galileo is credited with their discovery, there's some controversy around this. Galileo received a letter from a fellow scientist asking him whether the phases of Venus were visible through his new telescope. Shortly after, Galileo wrote his own letter to Johannes Kepler explaining his observation of Venus going through phases, but gave his fellow scientist no credit. Interestingly, Galileo's letter to Kepler was both in code and an anagram, rather than a plain statement.
Instead of saying something like, "I have observed Venus going through phases," I wrote, "The mother of love imitates the shape of Cynthia, the mother of love being Venus, and Cynthia being a popular allusion to the moon." I then scrambled this into an anagram, meaning these are now too young to be read by me.
This method of encrypting discoveries meant Galileo was protected from Kepler publishing before him and trying to take credit for his work, since Kepler wouldn't have known what he meant, but also gave Galileo written proof of his observations. This provided crucial evidence supporting the heliocentric model, where the Sun, rather than the Earth, is at the center of the solar system. Later in the 17th century, Isaac Newton revolutionized telescopes by developing the reflecting telescope, which used mirrors instead of lenses. Reflecting telescopes had several advantages, such as clearer and sharper images, especially for observing faint and distant objects. Newton's design allowed astronomers to see more details of distant celestial bodies, such as nebulas and galaxies, that were invisible to the naked eye. Despite their capabilities, telescopes on Earth face limitations due to the Earth's atmosphere. Atmospheric turbulence can distort and blur images, while certain wavelengths of light, such as ultraviolet and X-rays, are absorbed by the atmosphere and cannot be observed from the ground. This limits the clarity and scope of ground-based observations, prompting astronomers to consider alternative solutions. To overcome atmospheric limitations, telescopes are placed in space. The Hubble Space Telescope, launched in 1990, orbits above the Earth's atmosphere, providing clearer and more detailed images of space. It can observe in ultraviolet, visible, and near-infrared light, revealing phenomena that are otherwise hidden. Hubble has made significant contributions to our understanding of the universe, from measuring the rate of its expansion to observing distant galaxies and nebulae. By avoiding atmospheric distortion, space-based telescopes offer a more accurate and comprehensive view of the cosmos. Besides optical telescopes, astronomers use various other instruments to study the universe. Radio telescopes detect radio waves emitted by celestial objects, allowing us to observe distant and mysterious phenomena such as pulsars and quasars. Pulsars are rapidly spinning stars that emit beams of radiation, while quasars are incredibly bright and distant objects powered by supermassive black holes. Although we won't go into detail, these discoveries help scientists learn more about the universe and its most extreme objects. Radio telescopes also detect cosmic microwave background radiation, which we'll examine further in an upcoming lesson. Infrared detectors reveal heat emitted by objects, enabling us to study cooler and obscured regions like star-forming nebulae. Additionally, X-ray and gamma-ray observatories detect high-energy radiation from sources like black holes and supernovae, providing insights into the most energetic processes in the universe. These tools complement optical observations, offering a multi-wavelength approach that enhances our understanding of celestial objects and phenomena. New observatories and instruments are constantly being developed to probe deeper into space. For example, the James Webb Space Telescope, launched successfully in December 2021, now observes the universe in infrared with greater sensitivity and resolution than its predecessor, Hubble. Ground-based observatories like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will soon provide unprecedented views of the universe. Additionally, NASA's Nancy Grace Roman Space Telescope, set to launch by 2027, will revolutionize our understanding of dark energy, exoplanets, and more, offering a wide field of view to capture vast areas of the sky in each image. These advancements challenge existing theories and lead to new discoveries, pushing the boundaries of our knowledge. In today's lesson, we delved into how observation methods are crucial for understanding the nature of the universe. We understood how, despite the vastness of the universe, observation, measurement, and analysis enable us to understand its nature. We traced the history of astronomical observations, noting how early civilizations laid the groundwork for modern astronomy. We explored the significant impact of technological advancements in telescopes, including Galileo's refracting and Newton's reflecting telescopes, and discussed the limitations posed by Earth's atmosphere on ground-based telescopes. We examined the advantages of space-based telescopes, like the Hubble Space Telescope, which provide clearer and more detailed images by operating above the atmosphere. Additionally, we looked at other observational tools such as radio telescopes, and infrared detectors offer a multi-wavelength approach to studying the cosmos. Finally, we highlighted the evolving nature of astronomy, driven by ongoing technological advancements and new instruments. Overall, understanding these observation methods enriches our appreciation of the universe and the continuous scientific efforts to uncover its mysteries. Watch the rest of the GCSE Physics course at Sophos Education.